Yes, so my name's Ellie, and in my spare time I build machines out of software. And I've been doing that for a lot of years. I've been doing that for about 35 years, in fact, and I know I don't look old enough to have been doing that for 35 years, but I've been doing it for 35 years. It's amazing how well preserved you can be when all you ever get is a screen glare tan. So, yeah, this talk is going to be full of code, in Go and C. And I'm going to have to remember the two languages quickly as I switch between them to be able to explain the C, because I don't program in C very often anymore. I've massively got into steampunk music recently, and this just seems to really sum up what this talk is about. I'm a languages geek. I always have been. I like knowing how the internals of them work. And I think it's awfully good fun to know how the internals of a language work, because then you can build your own whenever you feel like, even if you're never going to use it for anything practical. And we have a little philosophical section at the front here, which I wrote for RubyConf. And I don't normally do philosophy in talks, so this won't take long. So basically, we write software, and software is the point at which we and machines meet. But more to the point, it's the point at which our thoughts and machines meet. And as programmers, we spend an awful lot of time thinking about the thinking part of that, and coming up with processes to govern the thinking part of that, and ways of making sure that the other people we're thinking with are thinking in the same way we are. But we don't think very much about the machines at all anymore. When I started out, we talked about the machines a lot, because the machines were very limited, and if we wanted to get anything done, we had to understand them. So we like to style ourselves philosophers and wizards, and in the modern world, it's very easy to appear like a wizard. Oh my God, I just made this mobile device do this amazing thing. But really, it's all just smoke and mirrors. It's a bit of JavaScript and some CSS in an embedded web page, in a web controller, in something. It's not magic, and it's not philosophy at all. And our machines need something slightly different from us. They need us to be engineers and analysts. And by analysts, I mean psychoanalysts. Machines throw wobblies very, very regularly. Every time you get a stack trace or you get a core dump, that's your machine having a breakdown because you've asked it to do something that's quite irrational. And machines like us want to be rational. So this talks a little bit about machine philosophy, framed in a language we humans can understand, although of course C isn't a language most humans do understand, but Go's a bit easier to understand. And when I say also framed in a language we humans can understand, I mean, we're going to try and get ourselves into understanding how machines do what machines do. I can't promise to give you deep insight in this talk, but we'll go through the basics of how you can build little engines that you can go off and gain deep insight by talking to machines. So let's learn to love our little Turing machines. They're wonderful and they're amazing, and they can do all kinds of idiosyncratic things you'd never think that they should based on the rules they obey. And we're going to build some of these Turing machines in the image of other machines. So who's familiar with system virtualization? Okay, when most people hear the word virtual machine, this is what they think. Let me fire up a copy of VMware on a remote server, and I will inject an image into it, and it will pretend that it's a Linux box that's not really there. It's running on another Linux box that is really there. Oops. Hardware emulation is sort of a step on from that. Hardware emulation is actually saying, no, it's not just a Linux box in a box. It's, say, an Amiga in a box with all the hardware being emulated. And there are a couple of things in this slide that are here specifically because I love them, which is probably not the right thing to say in technical talk, but I just do. So over here, I used to have a Newton message pad, because when they became unpopular, they suddenly cost like 30 quid on eBay. And the MessagePad 2100 is just an amazing bit of hardware. You can run an emulator from MessagePad on your mobile phone really, really slowly. A quad-core modern ARM chip will be flawed trying to pretend that it's an old-fashioned 166 megahertz strong arm. It's amazing. This over here, this is not just an emulator. This is Doom running in an emulator of an open RISC-OS box that happens to be running in JavaScript in a web browser. With a working network stack, apparently you can do LAN party games in it. That's at the point where you've got to ask yourself, how far down do the turtles go? The answer is all the way. Obviously, some of us also have a passion for older machines that were actually useful. I was very upset when my last Series 5 finally gave up the ghost. But you can emulate it on a Windows box. I've got a little clamshell Windows tablet machine that really runs it very, very nicely. But this talk isn't really about those things. This talk is about something a bit more basic. Because I could do a talk on hardware emulation, but we'd be here for like 3 days, and we get really upset with, why does a timing circuit have to work that way? We're going to actually look in the insides of the machines that we normally program for. Because as programmers, every program we write is actually targeting a machine. And that's not our laptop or our desktop or our server. That's actually a language designer's idea of what a computer is. So here we've got 4 very popular virtual machines, 5 technically. So this is the one that is the granddaddy of most day-to-day commercial programming, the C VM. Nobody thinks C has a VM, but C has a virtual machine. It has a CPU model, which happens to be identical to a CPU. It doesn't bother to abstract it at all. It has main memory with frame stacks and heaps and things. And all of that's a machine. It's programmable. Every time you actually grab memory with a malloc call, a whole pile of things under the hood have to be done to actually get you that memory. That actually involve turning the idea of a page of memory into something the machine understands. This is the VM that I started out first programming and programming for, and that's the 4th VM. And 4th is different to C in that 4th has a stack and a dictionary, but it's still a very simple virtual machine. This up here, this is the common language runtime. Now, anybody who's a .NET programmer probably doesn't think they're programming a virtual machine either. You don't install anything like you do with the JVM. But actually, under the hood, there's this entire model of what a computer is that just happens to all be compiled down into an executable, rather than distributed as bytecode. This over here is what most people think of when they think of these kinds of VMs, the JVM, which is an amazing piece of technology on many, many levels, with one of the most appallingly simplistic and awful bytecodes ever invented. Because to the entire world using it, it looks like some cross between C and 4th. It's stack operations and things. But under the hood, there's a whole pile of tooling that turns that into efficient assembly language, and then turns that into a fast-running program. And this down here, this is the granddaddy of all functional languages. Because if you program for a functional language, you program for a virtual machine. It's actually very difficult to make a program not tamper with memory. So if you want to have a functional language in which things are immutable, you have to start off by having an abstraction that says things are immutable, because otherwise the machine will quite happily make them mutable. And this is called the sector machine for stack, environment control, and dump. And basically most of the functional languages you'll ever play with have a model of that underneath that can then be compiled down to something more efficient. I apologize for the graphics. These are all hand-drawn, and iPads are brilliant because you can draw on them, but at the same time, they don't necessarily encourage you to draw well. So this is basically my virtual machine, my virtual model of what the average computer looks like. So we've got a CPU with some registers. We have some stacks that CPU can make use of. Those are often normally mapped into the register space. But we can pretend there's something different because it makes it easier to think about some things. Far off up at the top, we have a heap. That's basically our normal RAM chips that are on our motherboard. And some kind of caching in the way because they're slow and our CPU is much faster. Over here, we have some kind of persistent storage. And we've got some buffers between that yet again, they're caches because persistent storage is very slow. And then down here, if we're network enabled, as we normally are in the modern world, we have a network connection that yet again, there's some buffers to cache because that's even slower than persistent storage. Now these little numbers up here, these indicate roughly how fast these different things are. And this over here, 10 to the minus 9 of a second, that's 1 nanosecond. That's the time it takes for light to travel thus far. Okay? It's often easiest to think of these things in terms of how far light travels. So, to get to that cache up there to talk to main memory, takes 10 of those laid out in sequence. That doesn't seem so bad. That is 10,000 of those laid out in sequence. That is bad. That's long. And this down here is 100,000. That's very slow. So a lot of what people are doing in a normal computer to accelerate the performance of a program is based upon leveraging properties of particular components to overcome the timing. Now we're going to start off by looking at CPUs. This talk has two basic chunks. One is, how the hell do you write a CPU in software? And the other is, how the hell do you manage memory in software? Now the bit on managing memory isn't quite so interesting, although there's some bits in there that I get very geeky about. The bit on this side, this is the side where you can actually sit down and you can just play, because it's very simple to put together a machine consisting of a dispatch loop, it's called, which runs that. So we're going to spend some time on that, and we're going to look at how to do that in C and Go. And then we're going to look at some popular ways of architecting what a machine looks like at that level. So I have tried to make this code as big as possible. It will vary in size as we go through, because some of it just doesn't want to fit on a slide as much as others does. But this here, this is a very simple C program based on an infinite loop and a switch statement. And all this does is it reads through a set of values, and some of them are operations, so it performs an operation, and some of them are values, so it uses those as data for the operations. Let's see. Structurally, this is a stack-based implementation of this loop, i.e. I've got a stack. I can shove things on it and take it off. I've not shown the code for that. In a later section, the code's there. And we decide that a program is nothing more or less complicated than a whole series of integers. So thankfully, C gives us enums, so we can make this slightly readable. So we've got push, add, print, exit. So it will stick 13 and 28 onto a stack. Then it will add them together. And this is a stack operation. So coming over here, it pops two values off, performs the calculation, then shoves the answer back on. There are some registers in here. This machine is actually quite advanced because I've got a left and a right register. So that when I'm doing the math, I can store the value that's the left operand in the right place and the right operand in the right place and do the math the right way round, which is quite significant if I decide to put negative numbers through and do subtractions, and I want to do things, or multiplications or whatever. I want to make sure I get them in the right order so I don't cock it up. I cock stuff up regularly. It's an important part of learning as a programmer, is to embrace that. So, and down at the bottom, to run a program, all we have to do is kick-start this loop. And once we've kick-started that loop, it will just run and run and run and run and run. If I hadn't put the exit statement in here, it would fall off the bottom, and then it would just sit there in an infinite loop forever, because this has no way of escaping, apart from an explicit exit. So this is an attempt to do the same thing in Go. Right, how many people here know Go? Okay, I will try to explain what's going on then, in terms of what Go's doing, as well as what the program's doing. So firstly, Go is a lot like C, but it has some slightly different conventions about packaging, and certain gotchas in Go and C don't exist in Go. This is a main program. You can just compile this and run it. Everything to run it is in there. An import just allows you to import something just like if you're doing an include in C. Yet again, the weirdest thing, I guess, in here is probably this. Oops, if only I had a laser pointer. That's far too high to leap. Right, so up here, where we're doing an interpret, we're taking a slice of something, and that interface curly brace pair, that actually means any value that Go knows can be passed in as an item in that slice. And that's because Go has a construct called an interface that has a set of, it's basically a method set. And what that says is, please give me anything, regardless of whether there are any methods defined on it. which means anything. So it's sort of like Go's equivalent of a void pointer. So our program looks almost identical, because basically it is identical. The constants over there, Go has perfect constants. That means at compile time, it looks at those, looks at where they're being used, and goes, they're probably integers. And then they're typed as integers. But they could explicitly be something else if I wanted, but I don't. I want them as integers. So it's an identical program. I've implemented a very simple stack using a list. The reason I've used a singly linked list is actually alluded to later in the talk on a subject called cactus stacks, which are a way of basically reusing older portions of a stack as part of expanding it. And they allow you to do things like snapshots, so you can keep the state of something at a certain point. But that's an implementation detail. The point is we have a stack and it does work. Over here, we have exactly the same thing going on. Now, I could actually have just made that a for loop without having any counter on it whatsoever, because Go supports an infinite loop. But in this case, I decided I might as well fold the program counter actually into the loop, because Go puts everything in the scope that it's declared in. So that program counter doesn't exist outside that loop. Yet again, we've still got left and right register. Everything is still doing exactly the same things. We're going through, we're checking the number, we're saying, oh yes, that's an operation, and then we're doing the things necessary. Okay, this is a very simple machine. Now, we can sort of vary how best to describe this. So boom, boom. There's the trouble with leaping from one programming language to another and then back again. So what we've got going on here is now I've defined some actual functions that do the operations. Right? So we call this technique back here, we call switch dispatch. We use a switch, we check a value, and we go and do a thing based on the value. But here we're now doing something called direct call dispatch. This is where what we actually want is a function pointer. We want to call a function directly. We don't want to go through the whole mess of working our way through the switch. Switch statements are relatively expensive, especially in C. So if we can avoid that altogether, we can speed things up. We can make dispatch faster. So in this case, our program now changes. Instead of integers, we're now storing function pointers. Now, to get round actually sticking integers in line next to function pointers, I've had to do a nasty cast up there, which isn't very pleasant, but does work. It does mean, arguably, if the program counter gets corrupted, it might try and call a function that lives at memory address 13, and that would not be a good thing. But obviously, you construct these things so it's not going to do that very often. There isn't really anything else to say there. I mean, the only difference is now we've got separated out functions. So this is how we do the same thing in Go. In Go, we have a slightly different situation. We can define user-defined types that actually have methods on them. So if I've got an interpreter type, I can run. Oh, where are we? Where are we? Where are we? Oh, I knew I could do that. Right. We can actually call run on the interpreter, just like in an object-oriented language. There are subtleties about this compared to OO, but it works. That's the main thing. So what we've got going on over here, we now say the interpreter carries its own state around. So it's got its own stack, its own program counter and registers, and a chunk of memory that contains the program. When we actually write the program up here, you'll notice that I can actually take any one of these methods I've defined on interpreter, and I can actually pass through the method rather than passing through the result of calling it. So now, to call these bytecodes is wrong, because a bytecode is really something that you use for serialization, that you turn back into this sort of stuff once you load it back in. And I should really at some point write a section about doing bytecodes, but it's just that's not a very interesting problem. It's something you have to port code around, not something you have to run it. So up here, to loosely call this a bytecode, our bytecode consists of either things that are executable or numbers. And now we're in a position where we can actually, at the runtime, decide that for itself. So let's see. So up here, where we're doing the run, or I could really do the laser pointer, we've got an infinite loop that every time it reads the program, if what's under the program counter is actually a function, it will call it. If it's not, it will core dump. It will say, sorry, you've made a complete cock-up here. There's supposed to be an executable function here. So now, the actual hard work of getting the numbers out is something that becomes a thing that the actual instructions that you've implemented as functions has to do. Right. Now, we can be a bit more clever in Go. Something we have in Go that we don't have in C is we have closures. And it's possible to program pretty much anything you can imagine using closures. I mean, once you're using closures, you're basically doing Lisp or Scheme sort of programming. And it completely changes the way you might approach representing a program. So I'm going to probably belabor some points here that will sound quite tedious to anybody who's not really into Go. But to start with, I've redefined what memory is. The actual program memory is going to consist just of function pointers. And I'm being quite sloppy here. I'm saying something that can take a pointer to the interpreter. We'll get rid of that in a minute. So now, if I want to store some data, rather than having the data in line, I can instead pass in a closure. And I can say, fine, the sole purpose of my closure is to make sure that I shove 13 on the stack. Let's update the stack. This, incidentally, is not functional programmer friendly because this is very immutable. What we're actually doing here is we're writing things that monkey with the internal state of this, and that's probably not a good idea, but it's a useful technique for playing. So this now consists of no data. This just consists of a stream of functions that will run and will do the various operations, some of which we could have as separate functions on there, and some of which we could. So let's see if we can get onto that. Oops. Right. So this is a variant of the same thing. It's running off of the same same structure over there. Only now, this is a bit, I have to turn my brain back on. I wrote that about 2 hours ago. And short-term memory is not my strong point. So, right, yes. So here, we're doing absolutely everything that's done in the interpreter, purely in our own code, and we're actually controlling the program counter directly from inside our own closures. We are basically treating our box like the biggest white box imaginable. Whereas if we skip back a bit with this, we're treating it like a black box. The only thing that can actually tamper with it is anything that actually lives in line, that's inside that class, that type. So, oh God. Right. So here's another variant that's doing something slightly different. Back here, we're trying to merge the two pushes. We have, over here, we have two separate closures pushing values on the stack. And here, we've merged that into one closure doing it. And that's kind of, it's efficient from my point of view. It's not necessarily very readable, but it is efficient. I'd quite like to be able to push an arbitrary number of things onto the stack in line in my program. This up here shows off the fact that in Go, a function itself can be a returnable value. So here, when I say npush 13 and 28, I create a function, a closure, specifically for this purpose, that it will make sure that it sticks 13 and 28 onto the stack. But if I made that 5 different values, it will create a function that shoved all 5 values onto the stack. So that's the deepest, nastiest bit of Go I'm going to show off in this talk. But it shows you that we're in a very different language to the one we were in normally with C. When people write VMs, they normally write them in C because it's a known quantity and it's got reasonable performance. And most virtual machines written in C, you end up buried in insane quantities of macros to make any sense of how to do anything. Whereas once you're playing with a language where you've got closures, you can pick up your copy of structure of interpretation of computer programming languages, etc., and you can actually just implement those scheme-style patterns for writing interpreters, which makes about 80% of the boilerplate go away. So, yet again, down here, our program is literally just these functions in line. Now, I wonder why you're there. Boop, 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 boop. Oh, yes. So one of the things that's kind of never gets talked about by people who do talks on virtual machines is jitting. And I don't normally. Only last week I did a version of this talk in Ruby, and Ruby's got very different facilities compared to C or Go. And it just seemed quite natural as part of writing the talk to write an inline assembler, to essentially go through a program and replace some of the things in the program with other things, because it was like 5 lines of code to do it. So I thought it would be quite interesting to see exactly what would happen if I decided to JIT my Go program. So as a result, I've expanded what the Go program actually is doing. So I've introduced a concept called a label. Now, you can create your own types out of any type in Go. Once you've created your own type out of it, then you can do the quite traditional, boring thing of typing something when the compiler meets it to make sure it's got the right type and so forth. So I've added this table to the virtual machine that just contains labels. And that's a map of labels pointing to ints. So that's string pointing to integer, basically. Given this string, please give me back a number. And I've introduced the concept of loading the program. So when we do a program load, what we can actually do is we can go through, and for every single token we meet, we can say, can we assemble that into something else? And there's only there's only one thing we're actively looking out for. We're looking out for inline strings and that are type label, and we're going to use them to mark points in the program. The reason we're going to do that is because doing jump instructions just numerically means you sit there to get the right increment that you want to go in. So all will become clear over here, I hope. So I've introduced a jump instruction. And this jump instruction just says, if the top value on the stack is 0, jump somewhere. If it is 0, continue on. And so our program has now become considerably different. So this program no longer is doing addition. This is doing subtraction. It's doing counting down from 30. So it will run through. It will decrement the counter every time it goes to a loop. And to make that loop readable, I've introduced a label, decrement. That's the point I want to jump back to every time I do the loop. I'm still mixing in a combination of functions I've defined on the fly and methods that already exist on the interpreter. And these here, these closures, are set as values up there, but yet effectively, those and those are the same. It's just these don't have names. These can't be referred to again. When I get down here, if the stack doesn't have a 0 on it, I'm going to jump all the way straight back up to decrement. So if it does have a 0, I'm going to print out the state of the program, and then I'm going to exit. And if it wasn't for the fact that exit takes a parameter, I could find a way of doing that without actually having to bind it in the closure. But we've got actually a fairly rich machine language now. Pretty much any problem you can think of can be defined in terms of additions, if you're allowed to have negative numbers for the additions as well, and jump if not 0. There's a whole subclass of computing devices that those basically are the only operating instructions you would have that can do pretty much anything you want because it's still sufficient to effectively be a Turing machine. It's just it wouldn't be a nice thing to program for. So we won't. Now, up to this point, we played with tricks that we can do in both C and Go. Unfortunately, there's only so far we can go in Go on optimized dispatch. C's got a particular little trick in its arsenal that was introduced by GCC and that's now supported by CLang. And that's the ability to define labels in a function and actually take the address of them. So that now, where everything up until here is all based on calls, to a function call, now everything can be based on local jumps, which are much, much faster. This doesn't involve shoving anything on the stack. It literally just involves jumping to a location, to a location, to a location. And we have a very simple little interpreter here. It's actually built into the interpreter is a dispatch table consisting of the addresses of the particular things that we're going to call as opcodes. And a program still looks identical to the way it did in our C program to start with. It's still just basically a stream of integers, only now these get patched to be those jump addresses. They're offsets into the dispatch table. So now everything is happening locally. This shaves a surprising amount of time off of program execution. Because on modern hardware, every time you have to do a function call, you effectively are invoking the branch predictor. Because the branch predictor has to figure out whether or not doing that function call is now going to load a whole new pile of branch states and stuff like that. So actually, you've just shaved a huge amount of cost on modern hardware off of doing what you're doing. Although that's not how most people think about this when doing it, because we don't really tend to think about how our hardware works at that level. So this is indirect threading for the simple reason that we're going to the address that's defined in the dispatch table. So we're doing a lookup in the dispatch table each time. We can actually go further in C. We can actually go to direct dispatch. Now, basically what happens here is for each opcode, we can actually say, well, you've got the program counter. So you know exactly where in memory you are. So literally just do a go-to based on what's in memory now. It's very difficult to visualize this, except to think of it as a series of threads that you're following. Some of those threads, it's a case of I've got the thread and I just go straight down it. That's what direct dispatch is. Whereas with indirect threading, I've got a thread, and at each knot, it tells me to look on another thread, and then I follow. So as you can see, the one is branching up and the other is going in a straight line. That's as optimal as you can actually make dispatch in C. And it's probably as optimal as you can make dispatch in assembler as well. So if you're writing a really, really high-performance virtual machine, this is what actually sits in the heart of whatever's doing your instruction dispatch, this kind of thing. Now, to make it a little more real world and also a little easier for me to understand, most of these things end up with macros defining them, so that you don't actually write in terms of a whole pile of raw operations, but you actually write in terms of the macros. So over here, I can define for the interpreter primitives for doing push, for doing add, and doing print. And then I can give them this particular macro construction takes the addresses those are at. That can be made to go away, but just didn't have enough time to really care, is the truth of the matter. We can go actually further when we have this model. We can actually compile the program to just the raw jump addresses. See, back here we're interpreting. We're stepping through the jump addresses, but we can actually compile it down to just the raw jump addresses. And the way in which this is constructed, oh, come on, there's got to be the bit of code. No, go back, bit of code. No, I've clearly not put the bit of code on there that should be on there. Oh, yes, I have, up here. So what happens is you run into the compiler, and then the compiler runs down into the interpreter and works out all the addresses. The first time I tried playing with this, I created the most phenomenal quantity of seg faults, because these label addresses, they too tend to be the same across invocations. But they're the same within the context of that function's actual loaded memory address. So they're offsets relative to it. And that function won't always be loaded at the same point, which means it's quite easy to write, if you do the compilation the wrong way around, if you do the compilation, lift out the values, and then put them back in again, you end up with seg faults because you're accessing memory that no longer exists in your program, sometimes. And it's a timing issue as to whether or not it will still exist or not when it does it. But it's a weird sort of situation. Now, dispatch loops are all well and good. They give you dispatch. You get you can write a machine that does arbitrary things, and you can write a stream of tokens that is a program that will trigger those arbitrary things, and you can script it. I mean, the whole point of a dispatch loop is it's scriptable, but it's not a machine in its own right. It's just the trick of how do you get the next instruction and do something. So I'm going to walk through some fairly simple architectural machines, and I think I'm only going to do this in Go. I hope so. I don't like reading C code anymore. So first up, we have a harness, a virtual machine harness. And this has to do certain things. We want to be able to load a program, so we can do that whole assembling and patching up labels thing so that we've got jump addresses. And we want to be able to actually run a program which consists purely of working through the PC counter, incrementing it up until we stop the program. We've done something a little odd here. By default, the code up until now has assumed that the PC counter starts at 0. Because in Go, when you create a new value, it's initialized to its 0 value. So an interpreter would automatically start with its program counter at 0. But for certain operations, jumps, etc., it actually is nicer if you start at -1 and you start by incrementing the program counter rather than reading the first instruction and then incrementing. It makes sense in the code. It's not easy to describe. So the most basic kind of computer you can get is a stack machine. This is basically the abstraction that JVM uses. A stack machine just consists of a stack and something that can run operations. All the operations refer to data that's stored on the stack. It's got the advantage that you only have to worry about one place to access. But it's got the disadvantage that anything you want to do, you have to put things on the stack and take things off the stack. And stack handling is actually quite an unpleasant pastime, unless you've already got somebody who's ridden your stack and abstracted it nicely for you. But then you don't get performance, and often what you want in VM is performance. So in this case, we've got a stack machine that's got, let's see what we've got going on. So I'm taking advantage of a particular property of Go, which is that you can do something called type embedding. Now, if you come from an OO language, you'll be familiar with inheritance. And many people who come to Go look at type embedding and they go, that looks just like inheritance. And it's the exact opposite. It's actually composition of something with a component inside, rather than this is a thing, subclassed. So up here, a stack machine contains a virtual machine. That doesn't imply that a stack machine is a virtual machine. It contains a virtual machine. So a stack machine already is scripting it at a lower level. And I've also decided to define slice of int as a type, because then I can embed it directly in the stack machine as well, rather than going s slice of int. And there might be times in the future where I might actually want to put methods on that slice of int. But that's going to be our stack. We're just going to use a growing and shrinking slice of integers as our stack. So the previous stuff, yeah, we're going to avoid. We have a couple of simple operations. We can push stuff on the stack. I haven't got a pop because it's not relevant to the program, but pop is very easy to implement if you do want it. And we've got an add. So we'll add the top 2 items on the stack to produce a top 1 item on the stack, and we'll chuck away the spare cell. So that's what this is doing. It's a horrible bit of code. One thing I don't like about Go is it doesn't have an easy way of referring to the final elements of a slice. Many languages don't, to be honest, but it's just really annoying having to take the length of something when there should be a simpler way of doing that. Yet again, we've still got our jump if not 0. And our program, we've defined a couple of things here. We've got print state, which will just tell us what's going on in the program. That literally will print out whatever the state of the VM is, and also whatever the state of the stack is. And yet again, when our program is identical to the previous one, we're just going to push 13 on the stack, define a label we can leap back to, push a -1 onto the stack whenever we jump back, and then just keep adding -1 to 13 until it's 0, and then print out what the state of the VM is. I'm now going to switch briefly to a terminal to demonstrate this running, on the grounds that people do like to see things run. And unfortunately, I have a ridiculous number of code fragments that got me to the point of having that. And let's see, we need to move this over here. Oh, that way. Boom, boom, boom. Boom, boom, boom. No, don't want you over there. I want you over here. We want the terminal over there. So, boom, 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 boom. There we are, and so where do we want to go? Come on. Right. Stack machine.vm.go. Boom. So this here, that's a program counter. Every time it's doing the print state, it's doing the first one in the subroutine, in the loop. And that's not very readable, but that's a 4. Let's see if we can make that a bit bigger. We've got a program counter. We've got the entire program that tells us that when we do our loop, we loop back to position 1, which is back here, and that would then be incremented automatically into here and do the next thing. We know where our labels are because we've got a table of labels, and this is the state of our stack, which only contains 12, because it had 13 and it's lost 1, and then each loop through, it's counting down until it comes out the end. So, boom, boom. Boom, 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 boom. Right. Stack machines are very easy to implement, and they have the advantage they normally end up quite efficient in terms of how much bytecode you have to do a program, because all you're doing is shoving things on a stack, taking things off a stack, and all the operations refer to the stack. You never have to put in anything to refer to anything else. But stack machines are also annoyingly slow. Oh, we shouldn't have that in. We shouldn't have that in at all. That's Ruby. Which makes me wonder what I did with the piece of code that I thought I put in that slide. You know what? We do it in Ruby. Why not? So, it's the same program, basically. Only in Ruby, we have the advantage we have symbols, which means that I can just use symbols inline, and the runtime takes care of figuring out what the hell that means. It's pretty much the same structure, except now what we've introduced an accumulator. Now, an accumulator is a single memory location that all operations occur against. I can put values on a stack in this particular example, but I don't need one. The Go version, which is lurking here. Boom, 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 boom. So let's have a look. Oh no, that doesn't do that if I do that. So Go version. Boom, 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 boom. Take the font size up a bit. The Go version, I haven't bothered with a stack. A stack is unnecessary in an accumulator machine because I can inline everything. So, oops. So coming down here, my program now has a slight difference in how it gets data in. It does a load value. Load value shoves something onto the accumulator. I've also got the ability to do a direct add. I can give it a value, and it will add it against the accumulator. So now I can inline adding and various other things. The jump if not 0 now cares whether or not the accumulator is 0. And this all runs off and it does the right thing. Accumulator machines are somewhat limited because unless you've actually got a whole big chunk of memory you can store values off to. So you already start to get into the place where you want to have a way of storing values into memory, which, to be honest, with stack machines you don't need. With stack machines you can actually get by without ever having any memory. It's just a question of very slowly doing stack manipulation. Accumulator machines tend to not be real-world machines. But, if we go back to here, and I think the code is much nicer in Ruby than it is in Go. To be honest, that actually, writing this last week for a version of this talk I gave, made me happy. In fact, I did everything over to Ruby in a day, and it made me very happy. But obviously, Ruby is not a high-performance language. So you don't really want to write a virtual machine in Ruby, although there are some emulator projects. There's a Game Boy emulator written in Ruby and a Super NES emulator written in Ruby. And they both work perfectly because modern hardware is so fast. Remember, for most things, light is only traveling that far. And in fact, on my MacBook, when I access a register on my MacBook, light is only traveling that far in the time it takes to access the register. That's phenomenal. You can't get much more efficient than that. We may be finally needing to actually genuinely do multi-core. So, register machines introduce the idea we can have more than one register, because an accumulator is a register. So I've defined a machine that's only got 2 registers, because for most real-world purposes, 2 registers is fine. You'd have a stack, and you can store off the state of the registers on the stack if you need to play with the registers differently. But our language has changed again. We've still got the ability to load values, but now we have to say which register we're going to load a value into. However, once we've done the load, that's it. It's loaded. In the previous examples, every time we wanted to set up doing the addition operator, we had to load -1 again into something, either onto the stack or whatever. Whereas here, I never have to load it again. It's in that register. I can just keep referring to the add in terms of that register. So in this case, I'm adding register 1 to register 0, and register 0 is actually decrementing by 1 each time. So register machines, this is why register machines are popular, because it takes away, it speeds things up. But on the other hand, it also creates bigger bytecode. This program is now considerably bigger than it started. And on average, you end up with about 40% more instructions for a register machine than you do for a stack machine. So you get bigger bytecode, but you get faster programs. I'm trying to think if there's anything here that's actually interesting to talk about, beyond the fact what it is. I ended up having to implement my own little wrapper for reading a value, because obviously there are places where I want to read in values. And in fact, this down here, these could both be inline directly rather than having them out separate. That's an artifact of the fact I was debugging this 45 minutes ago. So, the point about the architecture of virtual machines is once you can define registers in terms of whatever natural primitives make sense to you. Now, sometimes people do odd things. When the Parrot virtual machine was first being discussed for Perl, they actually discussed using Python objects as the registers, which is kind of like, but Perl isn't at all like Python, and I'm not quite sure why you'd want Perl objects to look like Python objects. But the point is there are many kinds of machines that get used outside the context of normal registers. Registers are like Z80s or 8086s with no extensions. We all, in our day-to-day hardware, we're actually using CPUs that are vector machines. So, I mean, there was a day, back in the day when Seymour Cray invented the idea, it was like 128 bits. Wow. 4 numbers packed into a vector, and it's so fast. We can do that in software. I mean, if we want, we can define our registers so that each of them is an array rather than just a scalar value. And then an add would add 2 arrays. So we've actually taken most of the dispatch loop cost out of adding, say, 10 numbers, because we just put together the 2 sets of 10, and then we just add the 2 arrays. Matrix machines are sort of, you're entering into territory like languages like APL at this point, where you're using higher order structures to be able to do mathematics on a grander scale. You also find extensions. There's a, God, is it BLAS for Fortran? Which basically gives you all of these lovely ways of using matrices in Fortran, because Fortran, if I remember rightly, does have a matrix type. Well, it's 20 years since I programmed in Fortran, I'm pleased to say. We can go further. So the City of London has lots of people who are engaged in financial transactions and massive amounts of market analysis. Most of the big trading houses in London actually build machines in terms of hypercubes. Hypercube, I mean, a matrix, most people think of a matrix as a 2-dimensional set of data values. A hypercube is when you decide to turn that into an n-dimensional set of data values. And a whole pile of things become much easier to reason about if what you're actually doing is mashing 2 hypercubes together than individually going down dimension by dimension to do it. And if you want to get really sick and weird, there's no reason why you can't define your processor purely in terms of graph operations. Now, the closest I can think of to a real-world example for that at present is SQLite. Now, SQLite has inside it a really nice little virtual machine. It's actually the best one to pick up a code base for and read because it's the cleanest. As in, there's no stupid tricks in there, there's no obfuscation, it's just a beautifully clean code base. And it's running relational algebra. So a lot of its opcodes, effectively, you're starting to do graph math. So the point is that if you can think of a problem where you want to do something, and you can define a type that describes naturally the thing you want to do it to, you can actually build a virtual machine in terms of that type. And then you can play with all kinds of barking mad ideas, and instead of wasting your time on the plumbing to do it, you do the plumbing once, and then you can spend all your time writing programs that work in terms of those primitives, which makes it much easier to do quick research. Now, I'm going to rush with memory because we probably haven't got time. In fact, I think we're supposed to have stopped now. So all I'm going to do is talk about this slide, and I'm going to show a couple of slides at the end that are references. So memory itself is an interesting area. The slide deck includes an implementation of something called a cactus stack, which is actually a really good way, if you're doing a functional language, of doing all your data types, because it gives you immutable history and stuff like that. But memory falls into two basic traditional architectures. Von Neumann, which is what we're all familiar with, where we're interleaving data and code, and our stacks and our heaps run in the same memory space. And Harvard, which for anybody who's ever done embedded programming, embedded systems nearly always a Harvard architecture because you nearly always have a ROM and a RAM. And the ROM contains your code, and the RAM contains your live state. The thing about writing a VM is you can implement memory models that are different than the actual memory model of your machine. You have to make sure you get your math right and that you do things correctly. But the point is now you can try out different ways of not writing bugs. So Forth, for example, splits off data and control. If you write a C program, your stack gets used for both data and control, i.e. if somebody can overwrite a stack frame, they can cause your program to jump back to a place you don't want it to go. That's basically the trick that lives underneath things like continuations in Lisp, is that you can basically monkey with the stack. But if you want, you can actually split stacks, so that can never happen. And this over here, this would basically be all three of those models can be condensed down to this, where you have data and control stacks separate, so nobody can break your stack, and where you have code and data separate. This is basically up here. It's the same as having the NX bit enabled on Intel, where you basically can't execute code in a page because it's data, and the processor knows that. You can do that for yourself in your software. So, right, let's... Well, where are we going? Where are we going? Right, here we are. Oh, I hate the way it does that. Boom, boom, boom. All right, so there are some... Go on. Other resources. Firstly, Go has a way of wrapping C functions, so you can call them directly from native Go. So if you have a little virtual machine written in Go, and you want to play with something that's in a C library, it's very easy to do. You literally can inline a lot of the C as comments, and it's got its own mapping on the type system so that you can call stuff. There are several good resources online, but I happen to know Andreas quite reasonably well, and he's written a really nice resource on it. You can also use assembly language from Go. That's not very well documented. There are a few snippets around. That was the best of what I could actually find as a reference. I found this video last week, and this really is around, this is nothing to do with VMs. This is about writing optimized code in games. But it covers all the basic things that if you're designing a VM, you start thinking about. Symd instructions, so that's vectors. Branch prediction, because underneath the hood, the process is doing branch prediction tricks. But sometimes you can statically analyze bytecode, and you can effectively predict how it's going to run. Cache misses, so how you deal with the fact that caches aren't always reliably laid out the way you want. And memory latency, which is the single biggest annoying thing in the world. The source code for this talk lives here. The latest code hasn't yet been pushed, but the stuff through Ruby is, so Ruby and C are there. And finally, there are 4 books I always recommend for anybody who wants to play more. So this is massive. Well, I'm trying to think. I don't think a single one of them is in print now. This one might still be in print. This is a tediously dull book intended for people who want to learn in an academic way about virtual machines, but it has about 3 or 4 chapters that are relevant to writing your own little VMs. And while I say it's tediously dull, it's also surprisingly comprehensive. This was a book released in the 70s that basically, a threaded interpretive language is, by any other name, Forth. Languages that just thread and thread and thread execution. And it's fascinating because it's got lots of little diagrams that are very good for reading it. It's available online as a bootleg ebook. I think it is somewhere available as a purchasable one, but I can't remember where. this was the original book that Sun released explaining how to write Java assembly language. And it's fascinating because A, Java assembly language is a very simple assembly language, and B, because it also tells you a lot about how things like strings, etc., really are laid out in programs. So that's a useful resource for getting an idea of a real-world bytecode. And this is my all-time favorite computer science book. It's just 10 chapters about implementing different languages. It starts with an S-expression interpreter that isn't even Lisp yet. I think it does Lisp and ML and Smalltalk and Clue, Prolog, a couple of others. All the code is written in Pascal, which by and of itself is a bit weird, but is available. The code is available online in a C version, which I've never really liked the C port. It's quite ugly. It's also got 2 chapters, one on garbage collection and one on actually compiling to assembly language. So, it's difficult to get hold of. There isn't an ebook copy of it, unfortunately, but it's the best book I've ever come across on the subject. It's much better than anything that's got the word virtual machine in the title. Thank you very much.